Here's a fun question. Let's look at the heat equation. This is really a multivariable question, and one a little beyond the scope of our 123 class, but I'll start there. Let me grab the book here and just kind of remind you of this derivation. We were working in chapter 20 here about the transfer of energy. And one of those was the thermal conductivity, and this is the result we got. We got the result here that the energy flowing, the power, was proportional to, and then we have this K, which is the thermal conductivity. So it depends what kind of material you have. So it could be a metal bar here out of aluminum or lead or copper, or it doesn't even have to be metal. It could be styrofoam. But there'd be some number here, how well it conducts. A is the cross-sectional area. So if you could think of this in 3 dimensions and cut this bar. But here's the big part. This is the temperature difference between the hot and the cold side. And then L is the length of the bar. And so this is the temperature differential, if you will. You might even call it a temperature gradient if we're getting into multi-dimensions here. So this would be the change in temperature over the length. In fact, back on the page before they got there, this is how they wrote it, and they put it in absolute value. I'll drop the absolute value and put a negative here, and we'll start there. And so starting with what you've already seen from your physics class, I guess I would do this. I would say, okay, so the power, P, equals negative, and the thermal conductivity, the area of the bar, and then the derivative of the temperature with length here. Okay, so working from that basic idea, if you kind of maybe think of this as a little piece here of material, something maybe like this, and so maybe it's connected to something on this side as well as something on that side, where if I had a grid here, this edge would be at position X, and this edge would be at X plus delta X. And so giving this little piece of material a thickness of dx. And I might just ask this very simple question. What is the change of energy within this little piece of material? See, because energy from the left can flow in, or it could flow out. But then likewise, on the right, the same thing. Energy could flow in or can flow out. And so we might do something like this. We might say, okay, the net, and I'll just put NET under here, power flow, is a combination of what flows in / out on this end and what flows in and out on the other end. So using this equation, I might say, okay, this would be minus the thermal conductivity times the area, and this would be the derivative with respect to X at the temperature at X. And so if this is a positive number, energy would be flowing in. And of course, by positive, if we read the math here a little bit, if this temperature gradient is something like the little piece in here is hotter than there, dx dt, this would be higher in this direction. So the gradient, I guess, the higher temperature would be that way, and so with the negative, the energy would flow out. Well, not worrying about the signs, I just kind of wanted you to see here that, again, if this center part was hot and over here was cold, then my dx dt, my slope, if you will, would be that way. And then, of course, multiplied by a negative number means the power is flowing out, would be flowing that way. And hopefully that makes sense, because I would be losing energy from this little piece. Okay, now I need to subtract off the energy that would be migrating either in or out at a position of temperature at x plus delta x. And so same logic with the math. If maybe this side is also cold, so hot to cold, the derivative would go towards bigger numbers, so there, with the negative. Oh, I'm sorry, it's minus a negative. I forgot the negative there, okay. And anyways, that would flow to the right, and we would get the energy out. Okay, so this is the energy coming in or out at this location and at the x location, and this is the energy in or out at a slightly bigger position. Now, ultimately, I'll take the limit as delta x goes to 0, but this is a really good place to get us started. In fact, maybe it might be a little better if I write it this way. I'll factor out the negative, the k, and the a, and I might as well even factor out a derivative, dx dt, and then what you will have left here is a temperature at x minus a temperature at x plus delta x. Now, on this side of the equation, this then is the change in the, or it's the rate of change, it's the power. So this really could be written as a dq dt, because we've been using that symbol q for the energy, the heat energy, and this is that flow of that energy. Now, if you also remember this little equation, that Q equals to mc delta T, where this m is the mass of the object and c is the specific heat. And actually, maybe I should write it for a second as a delta T as its temperature increases or decreases. And I want to be careful with that delta T because I don't want you to think it's the same as this delta T. This is a delta T between 2 points in space, and this would be a delta T in 2 different moments in time where it got warmer and colder. Maybe just a better way of writing this would be something like this. I'll put it down here. A little change in energy of this material would be mc times a small change in the temperature of that material. So kind of thinking of this as a small little object that always has the same temperature. Okay. So then I could, put this together, and this would be mc dt over dt, so temperature and time. Don't confuse those 2 t's. And then over here on this side, maybe I'll do something like this. I'll put the negative into here, so this will be a k and an a, and I still have this derivative, and now that changes the order. This is a temperature at x plus delta x minus the temperature at x. Okay. And a little maybe subtlety in here, because ultimately I'm going to kind of take a limit of this as this object gets smaller and smaller and smaller, but maybe for starters here with the with the mass, I'll say it's the density of that material times the volume of this material. Now, the volume of this material would be, and I didn't really show kind of a 3 dimensions here, but I really need to get into 3 dimensions to answer this question about the heat equation. But maybe I'll just say this right here is some cross-sectional area A. And that's really what was meant right here as we said the power was flowing in. So this is this A. And that's why this makes this convenient, or one of 2 reasons why it's convenient. So let's write the mass as the density of the material times the cross-sectional area A times the delta X, right? So that's the volume. So right here, this right here, the density times the volume is the mass. So then we still have the specific heat. Then we have the dt, and the dt being the temperature, dt being the time. Then we have the thermal conductivity. We have the area. Okay, then we got this derivative, and we still have this temperature at x plus delta x minus the temperature at x. And so the area will cancel off. And the important part of this step then is to really move the delta x over to this side of the equation. Because then as we start dealing with our calculus and we say, okay, let's take this as this thing gets thinner and thinner and thinner, the limit as delta x goes to 0, that right there is a derivative. So here's our density of material, here's our specific heat, here's our d temperature, d time equals, here's the thermal conductivity. Here is the derivative with respect to x that we really haven't changed since the beginning. But then we have another derivative. So this is the derivative with respect to x of the temperature. And so right there is a second derivative. So this says that k times the second derivative of the temperature with respect to x would be equal to, and then we've got the density of the material times the specific heat, and then it would be the temperature with respect to time. Now, usually this is written with these kind of grouped together, so maybe I'll take one more step in this and say, okay, let's write it as how the temperature changes with time is then equal, and so here's the properties of the material, the thermal conductivity of it, the density of the material, and the specific heat of the material. And a lot of times then, let me make sure I don't skip over the second derivative. There really is the heat equation. But a lot of times we just group that together as one big factor. It's all factors of the same material. In fact, I would looks like a diffusion type of process. And so usually we just give this the symbol alpha. It is the combination effect of the fundamental properties of the material, right? How well does it thermal conduct? What is the density? What is the specific heat? So all of those together would be unique for whatever material we're working with, maybe aluminum. But when you put them all together, you get just a single variable. And that is the heat equation. And so the heat equation is saying how does the temperature at some point change with time? Well, it's related to how the temperature changes over the spacing of it. And so let's talk a little bit more about that. But this is then what we call the heat equation. Now, I only did it in one dimension. So let's come back here and say, now, what if I would have done this a little more, what I might say, more complete. Maybe I'll change a color here. But I'm hoping you can see in the same logic that energy was flowing in on the x-axis, I could have a discussion about energy flowing in on the y-axis. And so there would have been another term here, and it would have looked something like this. It would have been a minus Ka, and it would have been the derivative in the y direction, and it would have been the temperature at y minus the negative Ka, and then it would have been this derivative with respect to y of the temperature at y plus delta y. And we would have had yet another two sets of terms. So this is the net flow of energy along an x-axis, and this would be a net flow of energy along a y-axis. And I don't know if I can squeeze it in here. Maybe I'll put it down here. There'd be another term, minus Ka, and then how is it operating on the z-axis? And so this would be the temperature at z minus a negative Ka. And in the interest of time, let me not go back and redo this, but I'm hoping you'll see that for a term I did on the x-axis, there would be a set of terms on the y-axis and a set of terms on the z-axis. And so the area would be, of course, not the same area here, because the area that it flows here would be a YZ plane, whereas the area that it flows here, coming down the y-axis, that would be the XZ plane. And here, this would be the XY plane, which is why back here at this step, then when we divide, or we would really have right here a delta X, delta Y, delta Z in this equation. And for the X component, it would be a delta Y, delta Z, and the delta X would remain, and we would have a derivative with respect to X. But for this grouping of the Y's, the area would be the X and the Z, and that would cancel off, and then you would have a dy down here, and so you'd have a second derivative with respect to Y. And so what I'm getting at is, I guess right here, you would have a K, and you would have a second derivative of the temperature with respect to Y squared. And you would have a K times the second derivative of the temperature with respect to Z squared. If you did this as you really should, a completely multi-dimensional problem, which is why I'm doing this, because you're asking about math well, I guess it's 220. But in Math 200 and then into 220, you do these multi-variable functions, and we didn't go that far in our physics. We just did this. We did in one dimension. But 3 dimensions is really just doing one dimension 3 times, and that's what I'm trying to get you to see. So the final answer should really look like this. It should look like, how does the temperature change with time? Well, it would be some constants, and so there's that alpha that involves those 3 constants. And this then would be the del squared operator of the temperature. And that's probably how you're seeing it in your multivariable math class. You're seeing it as it should be, with energy be able to flow in the X, the Y, and the Z directions, and that would change the temperature as a function of time. And of course, in your math class, you are just learning really to solve a multi-dimensional equation, but this is a really good one and kind of the classic one to help students, because it is got 4 variables well, 5 variables counting temperature, but the 4 dimensions of X, Y, Z, and T. And so you have temperature that is a function of all 3 dimensions of position, but also changing in with time, and that's how they are related. So this is called the heat equation. And so solving that is what the math class is trying to teach you. Now, let me go one more step here, because it's kind of fun to maybe even just think about this equation. You've heard me do the phrase, read this math. What is this really saying? And so to answer that, let's look maybe first at the easier side, the left-hand side. This is saying, how does the temperature change with time? Now, remember also we're talking about a single point, because remember I took the limit back here. So if I had, something like this metal bar, and I'll just kind of do a one dimension first, but if I had some points in the middle of that metal bar, this side of the equation is really saying, how does that temperature change with time? Does the temperature increase? Does it decrease? And how quickly is it doing that? Well, that's where the other side of the equation comes into play. Now, there is some constant on that material, so the first term here is just how quickly this is going to change its temperature will depend on what this rod is made out of. Is it made out of aluminum? Is it made out of copper? Is it made out of lead? Okay, and that makes sense. It's part of the material. Okay, but that really doesn't get into the math. And so, so given a material, then what is this part really saying? And even though it's multidimensional, let me just remind you that, this really is these 3 pieces, dt, dx, second derivative of temperature with respect to y, and second derivative with temperature, with respect to z. And I just realized that now that I went multi-dimensional, I probably should have all partials in here. Okay. But ignoring 2 dimensions for a little bit, let's just come back here in a metal bar. You see what this is saying, this is a second derivative. And so let's go all the way back to Calc 1 and say, okay, what does a second derivative mean to you? And if you remember, the first derivative was the slope, and the second derivative was the concavity. How much is it curved? So a graph that looked like this, and so if this is the x-axis, this is the y-axis, and you had some function that just went in a straight line, its second derivative is 0. It has no bending to it. It has no concavity. Now, it does have a slope, but it has no bending to it. Now, something that looked like a parabola had a bend to it. In fact, you probably recall that if you set y equals to x squared and you take the second derivative, you're just going to get a 2. And so we would say it has a constant concavity to it, right? Its concavity is a constant value. Now, something that looked more like yx cubed, well, that's second derivative. Let's see, a 3 and then a 2 makes a 6x, right? Would be 6x. And so that would say the concavity is increasing. And so this x cubed function keeps bending more and more and more and more. And so that's, again, this bending to it. So that will give us a chance to read this math. Here's what I mean by that. if I were to take, again, this metal rod and maybe fix the end to some kind of, we often call these heat baths, where we say, okay, this is just going to be at a fixed temperature, T naught, and this will be T naught. Maybe it's a big bath of water and just room temperature, but it's so much water, we're going to say, look, it's not going to change. And over here, same thing. It's a big bath of water. It's not going to change its temperature. And if you made a profile and plotted its temperature versus the x-axis, and maybe you initiate this with, I don't know, maybe you put a torch underneath it. So the torch is near the center, and so maybe you have really no temperature, and then you have this massive increase where it spikes at a high temperature and curves down. Oh, what will happen? Well, this equation is saying here that the rate at which its temperature change is related to how much bending is going on, how much curvature is there. And so these places that would have, in this case, a high peak in its temperature would change quickly, whereas these other ones would change slowly. And if the second derivative, the reflection point, is right about here, okay, this concavity is negative, this concavity is positive. So looking at this, I would say that where the concavity is negative, right here, this is going to decrease in temperature. But over here, where the concavity is positive, it's going to, so positive, it's going to increase in temperature. So if I was doing kind of a time lapse of this, this would come down, and so maybe the temperature in the middle has cooled a little bit. But you see the edges have gone up. Now it would still go down to that same temperature, but maybe an interesting profile of the temperature I might have a little later in time might look something like this. Now again, we can play the same game because this is true at all moments in time and space. So I'm going to be looking at the concavity of it if I'm trying to read this. And so anywhere the concavity is then negative, it's going to be cooling down. And anywhere the concavity is positive, it's going to be warming up. So in this case, I can see that what was kind of a concentrated high temperature has now kind of spread out. And the high temperature is now cooled down, and the lower temperatures have risen. And maybe some energy has actually got a chance to flow out into the water, or maybe it hasn't yet. But playing the same game, it looks like I would have a concavity that would change about there. That would be a reflection point, and maybe another reflection point there. So now kind of this bigger area of the bar has a negative concavity, and so this is all going to cool, and this is all going to rise. Now, I kind of wish I wouldn't have put fixed ends here, because if there wasn't any place for the heat energy to go, the ends would build up. Let me do that. I know that's kind of changing the middle, but let's just say I had a metal rod without any place for the energy to go outside of the rod. Then, again, this would cool down, And this would, so now we would have just a kind of a smaller profile, and the ends would have warmed up. And again, I think you see now where I'm going. Now the concavity is a wider space of where the negative is, and eventually what you're going to get is a temperature profile, temperature position, that would have no bending to it, no concavity. Now, in this case, it would also be a flat horizontal line. But had I done something like this, had I done something where this side is really hot, maybe boiling water, and this side is ice water, and I just take a metal rod that's at room temperature, and I just jam it in there. So in that case, my temperature profile looks something like this. I'll just say I make contact, and so that edge is way up here at boiling water, 100 degrees. And this edge is, say, at 0 degrees Celsius. Now, most of the rod is probably somewhere around 22, 23 degrees Celsius at room temperature. So the profile would quickly go and mostly main at 23 and then shoot up to the boiling water. Okay. And in this case, again, if we take a moment to read the math, you'll see that we should focus on the concavity, the bendingness of this temperature profile, because that tells us the rate at which the temperature changes. And so coming over to here, you can see that there's a huge bend right here. And of course, it's a positive concavity, and there's also a huge bend here, which is a negative concavity. So this is stuff over here, and maybe you could even say at first there's no concavity. So maybe it's going to warm and do something like that. Those pieces all will warm, and these pieces will all cool. And so maybe now this is the temperature profile. And again, you can see how there would not be this dramatic change from room temperature to boiling water. Now we would have kind of a small area near the end of the rod that would start to feel warm, and a small area over here that would start to feel cold, whereas the center of the bar still is at room temperature. But again, going through this same logic, looking at the concavity, you would see that this would warm up, and this would cool down, maybe leave a little more bending to the profile. But eventually, you would get no bending to the profile. And at that point, there would be no more change in temperature. That's what this is saying. Once you have no more bending, no more concavity, you have no more temperature change. And so you would get a nice straight line where one end of the rod is hot and the other end is cold, and there is no change in temperature with time. There's no concavity. There's just a straight line temperature change from hot to cold. Well, I probably babbled on too much. Hopefully that was somewhat helpful. Oh, bye.